In case, so we have this week of content, next week of content, 1 week after spring break, and then we'll do our review and our exam on the 30th. So in exactly 4 weeks from today, we'll have our second exam. And then after that, we have about another month or so, another 4 weeks. Yeah, 4 weeks exactly. So yeah, I should be able to post the solutions for test 2 at least 2 weeks in advance or so of the final, so you can study that as well. We have this week, next week, we have 3 weeks of magnetism, and then after the test, we'll do 2 weeks of optics and waves and light. That should be hopefully interesting and relevant for you all. I'm excited to talk about those topics because they're very, very relevant for you all. Really easy connection when we get to lenses. Optics and interference is going to be lenses, and our eyeballs are lenses. So I'll be able to connect that to your eyeballs very easily. And then electromagnetic waves, we'll be able to talk about the different energies and stuff like that, and why it damages your skin, UV light and all that stuff. So it should be some interesting stuff. Mathematically, shouldn't be too bad. All right, so last class. Let's do a quick recap of what we covered last class. Last class, we'll call it main points from the first one. We talked about magnetic fields. Magnetic fields cause a force on moving charges. This force is perpendicular to the velocity and magnetic field. We'll put that as a sub-bullet point. Boom. No, that didn't work the way I wanted to. Boom. So that was the first thing we learned. We learned about magnetic field, the units, the variables, and we learned that the magnetic field is literally defined as a thing that causes the force of moving charges. That equation that we gave for it was F equals QB. F equals QB, B sine of theta, where theta is the angle between them. Always have a fun time going through the Greek alphabet and finding my symbols. Boom. And we learned that we use the right-hand rule to find force on positive charge. Force on negative charge will be in opposite direction, will be in the opposite direction. Okay, so we use the right-hand rule pretty much exclusively. That gives you the force on a positive charge, a moving positive charge. If you want the direction of the force on a negative charge, it is the opposite of that. So, magnetic field, force, and how to find the direction of it. We covered that. And then we also talked about a charge which moves perpendicular, good spelling practice here every time, to a magnetic field will move in a circle. So that was kind of the last thing we finished off when we talked about things moving in a circle. We did a problem or two on that. We'll do, I think, another problem on that today. And we reminded ourselves that the force, the centripetal force, is mv squared, something you all learned in Physics 1. Therefore, QVB, the force on a moving charge, is perpendicular, so the sine of theta ends up being 1, equals mv squared over r. You can set these two equal to each other, and that lets you find all sorts of interesting things. You can find the radius of it, if you know the other variables, and you can find the charge, the mass, all these different things using this equation, given all the other variables. So, that was a quick recap of basically everything. I didn't have a main point slide last time, so I just wanted to generate that real quick with you all together and have that up there. So today what we're going to do is do a few practice problems, just a couple more mathematical problem solving. And did I put this in a good spot? I feel like I didn't. No. Let me move this slide down to our last thing that we covered. Okay. We're going to talk about the force on a current carrying wire. The good news is we defined current as moving positive charge, so it's just going to be basically the same thing It's going to be very, very similar. So if you all felt good about the last content, the next step is just taking the next logical step. If you have one moving charge, and this is the force on it, one positive moving charge. Well, if you have a bunch of moving positive charge, we call that a current. And it's basically going to be the same equation with a couple of small changes to it. So we'll see that today. One thing I did want to point out to you all, one of the first things I started last class with was I told you all a magnetic field cannot make a charge move faster. That was one of the first things I told you all. A magnetic field cannot cause a force that causes it to move faster. All it can do is change the direction, hence a circle. It's going in the same velocity, but the direction is changing, hence the circular shape. So I started the class with that idea, but then at the end of class I told you all, hey, here's a cyclotron. Here's proton therapy and how it works, and there's this thing called a cyclotron here which speeds up the charge, and I said using magnetic fields. So I think I kind of contradicted the first thing I said with the last thing I said. So I wanted to explore that real quick and just kind of, it won't take too long, just show you all a better picture of that. So this does speed up protons, and it does use magnetic fields, and they do travel in circles. So all that was good. But let me show you a more apt picture, a more correct picture of what's going on. The magnetic field is making it go in a circle, but there's a tiny little gap. Imagine you took that cyclotron and you put a tiny, there is a tiny gap there. In that tiny gap is an electric field. That electric field speeds up the charges, and all the magnetic field is doing is keeping it going in a circle. So it makes it do a half circle, it passes the gap and gets a little faster. Oh, now it's making a slightly bigger circle. It swings back around, goes across the gap, gets a little faster, swings back around. The magnetic field is just making it go in a circle. And that circle gets bigger and bigger as it gets faster and faster. And at some point it gets fast enough that it kind of can exit here. And then that's when it passes through. We go back to our original picture. There's this kind of pathway for it to travel. Eventually it exits a tip into the patient. So, wanted to mention that to you all because there was a contradiction I mentioned. The magnetic field here is not speeding up the charges, it's just making it go in a circle, and then we use our electric field to speed it up. You don't need to know all that, but I thought it was important to clarify. I thought it was interesting, so I figured I'd share it. Alright, so let's get into some problem solving today. This problem, let me read through it first and I'll explain why this is an interesting problem. An oxygen-16 ion with a mass of 2.66 times 10 to the minus 26 kilogram travels at 5 times 10 to the 6 meters per second, perpendicular to a 1.20 Tesla magnetic field, and this makes it move in a circular arc. So a half circle with a 0.231 meter radius. What positive charge is on the ion? And what is the ratio of this charge to the charge of an electron? AKA, how many missing electrons do I have? So, the interesting thing about this problem is if we kind of had it flipped and we knew how much it was ionized, we could find the mass of that atom. Which, this is a way to measure masses of atoms, which are itty-bitty tiny things that you can't kind of measure in a direct way. You can't just put an oxygen atom on a scale and say, hey, there's its mass. This is a way that you can find its mass given all the other variables. So, let's go ahead and solve it. Let me go ahead and move my computer and make it very angry. It's very sensitive. All right. So, let's write down our, let's only make the word electron small. Which makes sense, electrons are small, right? Let me give myself a bit more space. I will draw a picture for this because it may help us understand what's going on here. Here we have our arc path, so it's kind of traveling in this arc. It's an oxygen atom. Sure, let's just chuck it right there. And we say the radius of this path is 0.231 meters. And we know its velocity at some point. If we want to put that on there, velocity, well, I'm not going to add any more there. I'll add the other details off to the side. So let's write down our givens. It's an oxygen-16 ion. Oh, let me check something real quick. Yeah, great. You all can still see my face. Wonderful. People online. Mass, 2.66 e to the minus 26 kilograms. It is traveling at 5.0 times 10 to the 6 meters per second. That's its velocity, because meters per second goes with velocity. 1.20 Tesla, that's the magnetic field, because Tesla goes with magnetic field. Our variable for magnetic field is B. That was one of the weird things. Oh, another fun fact, I learned why it was B. I Googled that. The answer is not satisfying. The guy that came up with this, his name was Maxwell. Maxwell had all these equations. And when he wrote his book on electricity and magnetism, he just decided, I'm going to label the vectors A through H. The first one I label will be A. The second one I label will be B. Well, the second one he labeled was magnetic field, and it was B, and it stuck. Not satisfying at all. But that's the reason. If you Google it, you'll find that for yourself. He literally was just going through the alphabet, and it just so happened that magnetic field got the letter B. Fun facts, right? Disappointing. The arc, the radius is 2.31 meters. Okay, so we have M, we have V, we have B, we have R. What are we solving for? It says what positive charge is on the ion? We are solving for the charge of this particle. Step 3. What equation has all of these things? This problem is a one-step problem. It's really nice when it works out this way. It's kind of always, if you don't know how to solve a problem, go with the hope and dream that it's a one-step problem, and if you just write down your givens and you write down the unknowns, and a lot of times they are one-step problems, especially on the multiple choice. The free response, yes, those are going to have more than one step, but the free response will have more than one step, but the multiple choice are often, if you just write down the givens and the unknown, you'll find an equation with all of them in it. So, we just went over the main points and one of the equations for traveling in a circle. And so one way is you could just look at this, look at the unknowns, find an equation that has all of it, or you recognize it's doing a circular motion and there's an equation for circular motion, and that's the one I just gave you. QVB equals mv squared over r. I can solve for Q. I'll do that in this step. So Q equals, I divide the V over, I divide the B over. And what's kind of nice is those V's will cancel a little bit. That squared will cancel, one of those V's on top will cancel with the V on the bottom. And I am left with mv over br. And that'll give me the charge. Just plug and chug now. So I'll give myself a new slide. Copy all that stuff over and plug in some numbers. And this is again, I always love this about this problem solving process. As you do these steps, you don't even have to look at the problem again. So I never have to copy it over. Everything I need is right here. Q equals 2.66 times 10 to the minus 26 times V, which is 5 e to the 6, divided by 1.2 times 0.231. Handy dandy calculator, nothing too crazy in this. No squares. Just some nice old make certain. The only mistake if you make it in this problem when plugging into your calculator is if you forget to parentheses the bottom. Always make certain when you're doing division that if you have two terms in the bottom that you are dividing by both of those and you're not just dividing by the 1.2 and then multiplying by 2.231. It's a classic mistake. All right, and with some rounding, because these numbers weren't perfect, so the number comes out to 4.797998, which rounds to 4.80 times 10 to the minus 19 coulombs. And you can see this answer is nice, because part B says, what is the ratio of this to the number, like to the charge of an electron, aka, what do I have extra of, protons or electrons, and how many? This is a problem that kind of showed up on test 1, showed up in the problem set. This is positive. The problem told us it'd be positive. So the question is, what do I have extra of, protons or electrons, and how many? That's what part B is asking for. Part B, what do I have extra of? I'll let you all spend a few seconds of thought. Is it protons or electrons? If you thought protons, great. We have extra protons. And how do I get the extra protons? The extra protons will be the net charge. It'll be Q. We'll put a cap. We'll put over the charge of just one single one. So 4.8 times 10 to the minus 19 over 1.6 times 10 to the minus 19. Those just cancel, and 4.8 divided by 1.6 is 3. 3 protons. 3 extra protons. It's really important that we don't think that an oxygen atom has 3 protons, because that would totally screw us up. 3 extra protons. Ta-da. So, this is an application, like a real-world application of this tool. You can measure the radius. You can launch some atoms. Now, again, traditionally what you end up finding is the charge-to-mass ratio, and you kind of ionize these things in a predictable way. So usually you're kind of more finding the mass, not the charge. And this is a way to kind of weigh, not necessarily weigh, but separate a bunch of particles into different masses. They'll each get their own, if you ionize them all the same, they'll each get their own radius, and you can see those different radiuses, and now you made a mass spectrometer. You've separated particles by mass, and you can distinguish what they are based on how much they arc, which is very useful for all sorts of different practices. All sorts of different things. So there you go. Circular motion. If this thing had extra electrons, this is just kind of a fun point to make here. So in my original picture, we knew it was going this way because we knew it was positively charged. It is fun to just kind of, I say fun, interesting that if this was a negative, it would go the other way. Fun fact. If it was negatively charged, it would go the opposite way. Remember, right-hand rule, they do the opposite of each other. Just mentioning that. It would have the same arc, though, assuming it had 3 extra electrons. So I don't want to confuse people and look at this later, but I do want to mention that just to reinforce that concept. Negative charges do the opposite of positive charges. Good rule to keep in your head somewhere. All right. More problem solving. A 3 microcoulomb charge with a mass of 3 micrograms is moving to the right with a velocity of 3 meters per second and a magnetic field that is pointed into the page. How strong must the magnetic field be so that the force of the magnetic field and the force of gravitational field cancel, i.e. the charge moves in a straight line? This is a more involved problem. It's nice, we get to draw a free body diagram. Yay, free body diagrams. Throw back to physics 1. So, we have our charge. Looks like it's a positive charge moving to the right. And it's got a mass, we'll write that down later. Moving with a velocity of 3 meters per second. And it's in a magnetic field that's pointed into the page. Oh. Nope, that's good. Before we even begin, I just did a check to make certain my problem was written correctly. And we're going to see why. It is written correctly. But let me think through, let's do that free body diagram. Which way does gravity act on things? This one you can answer because down, I saw someone gesture. Great. Force due to gravity is down. This problem says how strong must the magnetic field be so that the force of the magnetic field and the force of the gravitational field cancel. If gravity is down, which way does the force have to be due to the magnetic field to cancel it out? Saw someone else gesture. Fantastic, they gestured correctly. Upwards. I want you all to check if that's correct. Use right-hand rule and see if the way I set up this problem, if I made the magnetic field go in the right direction so that the force is up. Use right-hand rule and see if I did a good job. Velocity is to the right, magnetic field is into the page. See if you're getting a thumb that points up. If not, I did a bad job, and I also double-checked my work pad. But it's looking like a lot of people in the crowd are getting thumbs pointed. I say a lot. Enough. A few people. People whose hands I can see. Velocity is to the right. Again, I'll show you in just a second. To the right, magnetic field is into the page. My thumb points up. Woohoo! It does work. For those online, bam, bam, thumb is pointed up. That's important. If it did not point, if say my magnetic field was out of the page, we'd have a problem that would just make it'd be an impossible problem. So, great, picture, good. Let's go ahead and write down our givens. We have the charge, 3 microcoulombs, or sorry, 3 millicoulombs, so 3 times 10 to the minus 3 coulombs. We have the mass, and mass is always a fun thing to convert. We don't want to convert to grams. This is where, if you make a mistake on this is very likely what will happen. The mass here, I'll write 3 micrograms. We need to convert to kilograms, so it will not be 3 times 10 to the minus 6. That would be to grams. You know what? I'm going to write both. This is 3 times 10 to the minus 6 grams, but when we solve problems, unfortunately, mass is the odd one out, and it has to be in kilograms, which means we need to shift it another 3 units. So this will be 3 times 10 to the minus 9 kilograms. All of our math equations are built for kilograms. If mass is in it, it has to be in kilograms to get the right answer. Why? Because someone decided it at some point. That's our base unit for mass. I'd like it if it was grams instead, but I don't get to make the rules. All right, velocity is 3 meters per second. And there's another given we'll write down at some point, but I'll leave that mysterious for now. All right, how strong must the magnetic field be? We're solving for B. How strong must the magnetic field be? And I'm going to write in, no, we're not in step 3 yet. All right, so let me copy all these pictures over, give myself some more room. This is, I would call this a 2-step problem. We'll see why in just a second. Not much of a 2-step problem. It's not terrible. Step 3. I'm going to start. We want the net force to be 0. We want it to keep going in a straight line. If the net force is not 0, it will deflect. So that's something you got to pull from your mind from Physics 1. Because it is not, we want the velocity to stay straight as an arrow. Both of these things, if they are acting on it by themselves, would cause it to change. We want the net force to be 0. Free body diagram, the force due to the magnetic field is up. The force due to gravity is down. And I'm going to write this in a way that I think we always add our vectors, but FG is down, so it's negative. Ends up being subtraction. But I like to write it as up, as adding, just to keep things consistent. Okay, so we know we need to get, so here comes our, we got to get the force due to the magnetic field. That's QVB sine theta. And we're going to need the force due to gravity. This will be a fun memory test. Do you remember the equation for the force due to gravity? If you remembered mg, good on you. And that's where the given that I didn't mention before, what's g? 9.8 meters per second squared. Chuck that up there. All right. At this point, the worst part is done, and it's just plug and chug. So the trick to this problem, the challenge to this problem was remembering Physics 1, specifically that you have to do a free body diagram and that the force due to gravity is mg. So, let's do, step 4, I'm going to keep it in variable form. So, 0 equals QVB, and at this point, I'll just recognize that adding a negative is the same as subtraction, minus mg. I am solving for b here, so I just go through some algebra steps, add the mg to the other side, and then divide by QV to get b by itself. And at this point, it's finally just plug and chug. We know m, we know g, we know q, we know v. Chuck them in that equation, you'll get an answer. Something I may not have mentioned enough to you all is when I solve these problems, do not see that as a reason to not try these problems for yourself later. When you are going through the problem set, do not look at them and be like, oh, he already did this one, therefore I completely understand this problem. It almost, hopefully, by the end of me solving this problem, you're like, oh, that made sense, I understood what he did there. It's one thing to kind of see that. It's like looking at someone that draws a beautiful picture. Like, you watch Bob Ross and you're like, wow, look at him go. I see how he did that. It's another thing to do it for yourself. So, what I recommend whenever I do a problem like this, pay attention, write down this stuff, follow along, understand it. Try the problem fresh. Try the problem when you're doing the problem set problem. Still try this problem, but don't have the solution open. Try it on your own. Make certain you can do it on your own, because technically I will be here for you in the sense of I will be physically in the room during the test, but I will not be here to walk you through the problem like that. So, try it on your own. If you can do it on your own without looking at my solution at all, that definitely makes you understand it. If at any point when you're trying to solve it on your own you get stumped, there's a solution that you can look at to give you a hint of the next step. That's what I do these problems for. It's not to let you just be like, oh great, I can skip this one, I've seen how to do it, I completely understand it. The reality is, some of you may completely understand it the second I do this. Many of us may not, and the only way you can tell what camp you fall into is trying it for yourself. And if you understand it, it'll take you like a minute. If you don't understand it, it'll be really good to then try it, see what you didn't understand by actually doing it, and then getting that little tip, and then you'll remember it better, learn it better, and you'll be far better prepared for the test. So, I haven't mentioned that enough, but that's why I do these problems. I don't do them just so that you can see how to do it, and my expectation being that once I've shown you it, you completely understand. No, my expectation is that some of you will understand, but the vast majority will understand some amount of this, not 100, maybe 80%, 50%, 60%. And then when you do it on your own, you'll be able to look at this when you get stumped. When you're trying, you're like, oh crap, I don't remember that one step. You'll have this as kind of a guide to give you that next hint. Not to give you the whole thing, but to give you that next hint so that you can then learn it for yourself and actually confirm that you understand it. Again, like watching a Bob Ross video. He shows you how to do it, he goes through it slow, but you'll probably have to watch a few steps a few times to replicate his picture, and it probably won't look exactly like his at the first time, but you do it enough and you got it down. Things always look easy when someone else is doing it. If they don't, that's okay. I'm also here to help you. The end goal being that eventually it'll be easy, or at least doable. All right, great. So there's our two problems. Solved through. Now we can get to some of the new stuff. This was just some practice from the concepts we did last time that we didn't have time to solve. Good news is we don't have too many more slides to get through content-wise, so we'll have plenty of time. If we somehow do finish early, I'll kind of give you an intro to the next lesson. So it all works out. All right. So let's get to the new stuff. Oh, okay. Well, a little bit more practice. I lied. We love ratio problems. They're our favorite. Woo! No, y'all probably hate them. But they're good problems to do. They really test your mastery of using the equations and understanding how the various variables affect it. So, the previous example was clearly not that. The previous example, let me reword this. What happens to the radius in the oxygen problem if I double the strength of the magnetic field? So that was the one where there was the oxygen atom entering and it made that arc. What happens to the radius if I double the strength of the magnetic field? Use that equation, use your skills for how do we find these ratios. And I will tell you all, you're probably going to have to write this out to see the effect. So with every ratio problem, it's a matter of writing down the equation finding the variable that we're trying to determine what gets affected, and then plugging in the change. What variable is changing and what's that going to do to it? Based on the responses I'm seeing, I'm going to give you all a little hint. Here's my equation we're using. What variable are we trying to determine the change? It says what happens to the radius. What happens to the radius if I double the strength of the magnetic field? So the first step is going to be getting R by itself. R equals, find the variable that changes, change it, pull that number to the front. Alright, we'll go to 240, give you all like 20 more seconds. In 5, 4, 3, 2, 1. Alright, so before I show you what the answer is, before I show the responses, let's get R by itself. So I'm going to bump R to the other side. So RQVB equals MV squared. Divide everything else over. So R will equal MV squared over. I'm going to bump that down here because it's a little tight up here. R will equal MV squared over QVB. One of those will cancel, equals MV over QB, which is the equation we found before. So remember how we do these. What changes? It doesn't say the mass stays the same, the velocity stays the same, the charge stays the same. My magnetic field doubles, so I put a 2 in front of it. That 2 is on the bottom, so when I pull it to the front, it needs to stay on the bottom. And we can see here my new radius, let's call this R2. If we call the original R1, is 1/2. And so pretty good here, actually, pretty good. It halves. And conceptually, let's think about why that is. The magnetic field is doubling, which causes the force to double. And if the force is doubling, that's going to make the circle, it's going to kind of pull it in quicker. It's going to make that arc happen quicker. That force is going to deviate the particle stronger. You can almost think of it like planets. A planet that's twice as big is going to pull an asteroid in much quicker. That arc is going to be much smaller. So, the radius will double, that arc will be tighter. In a practical sense, that may be better or worse depending on your situation. Alright, so now we're getting to the new stuff. This is basically what the rest of it's going to be. If we look at this, we don't have too many more slides to kind of get through. So I'm optimistic that we may be able to actually start some of the stuff next week, which will be good, because I told you all the discussion questions needed. We'll see. So we had a single positive charge moving through it. We found the force, and it caused it to bend. Well, we just want a bunch of positive charges moving. We call that current. Current is moving positive charge. If moving charges experience a force due to magnetic field, current carrying wires do as well, because current carrying wires are defined as positive charge moving. Remember, the reality is that it's actually electrons in those wires moving, but we defined, and by we, I mean someone in the past defined positive charges as one moving. And so if you can find the direction that a positive charge will experience a force in the magnetic field, it's the exact same process for on a current carrying wire. The equation will look slightly different. But this is just a kind of a small step from what we just learned. All right, so here's the equation. It's a cross product, which we define as ILB. So same kind of thing. Looks very similar. Let's remind ourselves what the last one looked like. The last one was QVB sine theta. Here, replace Q with current. replace V with the length of the wire, and then it's still B sine theta. But almost very, very similar equation to what we did before. If you have a bunch of charge moving, the force on that wire depends on how long that wire is, because the longer it is, that's more moving charges. Every single bit of that wire will have some current going through it, so those will all experience a force. The larger the current, the more charges are moving through it as well, so the larger the force, and then the magnetic field is the one causing it. So if you think about each of these variables, more current, more force. Longer the wire, that literally means more charges are in that, so therefore the force is also stronger, because more charges are getting affected by it, and we still have that angle. We still use our right-hand rule, number 1, except instead of V, we have the direction of current. That's the only difference. It's the same exact rule. Just put your fingers in the direction the magnetic field's go, or the current's going, and same exact process. So, same rule. The force will still be perpendicular to it. And this is very, 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 very useful for us. Very, very useful for us. We'll see why by the end of these slides. But give you kind of a hint. We can take a magnetic field and make a wire move. We can take a magnetic field and make electricity move. So, we'll get to the punchline at the end. I won't spoil it too much. But very, 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 very useful. In my opinion, more useful than a single moving charge and the force it has on it. Here I just defined all the variables. I is the current, L is the length of the wire, B is the magnetic field, and A is the angle between B and, you can either call it L or I. The way it's set up is it's kind of L here, but it's the direction current's going. Just like it was the direction charge is moving. All right, practice. Right-hand rule number 1, y'all. Pretend that this is a magnetic field that's pointed to the left, a current that is going out of the page, out of the board, out of the screen, out of the whatever you're looking at right now. Find the direction of force. And again, based on the response I'm seeing, give you all a bit of a hint. Remember, your fingers should point in the direction of the moving positive charge. That's what current is. So your fingers should point in the direction of moving charge. And then they should swing towards the magnetic field. Your thumb will tell you the force. So point your fingers in the direction that the moving positive charge is going, which is current. Those are one and the same. Rotate your arms such that you can swing rotate your wrists so that you can swing your fingers towards B. There's only one way you can rotate your hands such that that'll actually work out, and your thumb will tell you the direction of the force. And always make certain you're using your right hand. It sounds like a silly thing to remind you all, but it's a real bummer if you accidentally use if you're right-handed on a test and you're solving this problem, you may be, oh, my left hand is free, I'll use that. Don't. You'll get the wrong answer. So that's why you may make that mistake. When you're solving these problems, if you're right-handed, you'll be writing with your right hand. You're like, my left hand's free, I'll just use that. Please don't. You'll get the wrong answer. All right, we'll go for till 2:25, and then we'll reveal the final answer. 4, 3, 2, 1. All right, so let's shake out our arm, get it nice and limber. All right, so flat hand, fingers point out of the board. Online people, I'll come back to the screen in a second and reveal the two of you. Out of the board, and I need my fingers to go swing to the left. They can't do that currently everything, so that's bad. So, your thumb points down. Now, nice little tip for you all that this may work that I thought about when I was going through these. Point your fingers in the direction of the current, and then just make your palm point in the direction of the magnetic field, and that'll also get you that same thing. That was kind of confusing on how to turn your hands to make it work, how to swing the fingers. Point your fingers in the direction of the current, your palm, if that points in the direction of the magnetic field, then your fingers can now swing in the correct way, and your thumb points down. So in case you're having challenges with that, that may be another way of thinking about it. So those align, your fingers point out, and then point your palm in the direction of the magnetic field so that I can swing my fingers that way, and my thumb points down. Again, in the problem set, there's literally there's 8 problems with a moving positive charge, and there's another 8 problems with moving current. So there's lots of practice in the problem set for how to do these. Please come, and if you're stumped on how to do it, come back, look at these ones. Who knows how good I'm doing with this webcam. But this is one of those things. Once you get it, you'll be good to go. It's just a matter of getting it. Getting that first little step. So let's do some maths. What is the force per meter? It's interesting. It's not just the force per meter on a lightning bolt at the equator that carries 20,000 amps perpendicular to Earth's magnetic field, 3.0 10 to the minus 5 Tesla field. What is the direction of the force if the current is straight up and the Earth's electric field is due north parallel to the ground? All sorts of fun things we can talk about here. One, never in your life will you ever see, so let's just draw a picture of this. Here's, the ground. Here's the lightning bolt going somehow magically straight up. The reality is a lightning bolt, wiggles and waggles. Let's pretend, for the sake of your sanity, that this is going straight up. It's the only straight up lightning bolt you've ever seen. There it is in all its glory. It's got a current of 20,000 amps. And we have a magnetic field. Let's say north is into the page. Let's say the magnetic field is into the page based on how I've drawn it. Up is up, north is into the page. Draw it however you want to. You've got lots of options. 3-dimensional pictures are hard, so pick a frame of reference and draw 2D. And B equals that. I'm going to write down the givens over here. So the current is 20,000 amps. The magnetic field due to the Earth is 3 times 10 to the minus 5 Tesla. And that's all you got. What are we solving for? If we really want, I'll leave some space. What are we solving for? We are not solving just for force. We're solving for force per meter, force per unit length. That is the tricky part in this problem. Force per meter is going to be the force per length. If you take the entire length of the lightning bolt, you do the force divided by that, you're going to get the force per meter. Length is in units of meters, force is in units of force, newtons. So how do we get the force per meter? We take the entire length, force divided by that. That is the tricky part of this problem. Now you know any problem you ever see. If I want the force per unit length, force per meter, F over L. Now you know. All right, step 3. What equation are we going to use? The one I just gave you. F equals ILB sine of theta. I'm even going to put that angle in there, and we will see what happens to that as we solve. And you know what? Let's get it in terms of our unknown. F over L equals IB sine theta. I just divide the L over. And it looked like we didn't have enough information, but we definitely do. We know I, we know B. And the angle between these, it conveniently tells us that it is perpendicular to that, which we could also tell from our picture. So we know that theta is 90 degrees. Sine of theta will be 1. That will go away. We'll see that when we plug in our numbers. So at this point, solving is pretty simple. The fun fact for you all, why did I define current as moving up? When you see lightning bolts, they look like they're going down, but you can't really tell. But if you've ever watched a slow motion video, because what is the thing actually moving? Electrons. The electrons go the opposite direction of current. The electrons are the negative charges moving down, which is mathematically the same as saying we have a bunch of positive charges moving up. So, current does go up in lightning bolts because the reality is it's electrons going down. Always nice to reinforce that idea. You know, I wish I could go back in time and make them define current as negative charges moving, but I mean, if I could go back in time, that's probably not the thing I would change. So, there's lots more things that are more important than that. All right, so plug and chug. F over L equals 20,000 times 3e to the minus 5 times sine of 90. Sine of 90 is 1. So, you know, if you're feeling really ambitious, you can try to do this in your head. 3 times, nope, not doing it. Maybe would have gotten close, but I probably would have been off by an order of 10 or something. I was to talk about this in office hours as well. It's nice to be able to do math in your head because it lets you kind of have an idea of what the answer should be. But my brain has made a lot more mistakes than my calculator has. So pretty much rule of thumb is I almost always plug things into a calculator because why not? I am not so prideful to think that my brain is as good as a calculator. And I am not willing to risk looking like a fool in front of 200 students. Well, let me rephrase that. I look like a fool plenty of times, but not because of my pride, hopefully. 0.6 newtons per meter. So that's kind of fun, and this is true. That's also another fun thing with this problem. Lightning bolts do experience a force due to magnetic field. Does that matter? Probably not really at all. They're so fast that any deflection that this would cause on it is probably negated by a whole bunch of other variables. So, you know, it doesn't really change anything, but it's fun to think about. The Earth's magnetic field is both weak and also impressive because it surrounds the entire Earth. So it's kind of, you know, it's a lot of it. And it's enough to move stuff everywhere around the Earth. So that's kind of nifty. But it is pretty darn weak relative to other magnets we could make. So there you go, there's a problem. All right, now we get to kind of the punchline. Not really any math here, all concepts. Let's make a loop of wire. And this is where we can start to see some interesting things happen. What are the directions of the force for each branch of the square loop shown below? The current is going counterclockwise, and the magnetic field is pointed to the right uniformly. It's the same everywhere. Okay, we're going to break this into pieces. That's how you solve this problem. You do each side of the loop, top, left, right, bottom. The net force will reveal itself, whatever happens to kind of each side. You can kind of, we'll build a picture for what it's going to do to the entire thing. So, what happens to the bottom? What is the direction of force for the bottom of the loop shown below? It's the same exact loop. So on the bottom, current is going to the right, and then everywhere, the magnetic field is going to the right. So we are just exploring what the force is on just the bottom section here. Each section of this loop will experience a, we're going to break down each piece. We'll kind of double down, but yeah. For now, what's the force just on the bottom? Is it into the page? Is it down? Is it 0? Or is it to the left? All right, we'll go to 135. And 5, 4, 3, 2, 1. All right, so your gut reaction will be pull out your right hand. But the problem is, remember I told you all one of the tricks, point your finger in the direction of current, and then put your palm in the direction of the magnetic field. Well, you can't do both. And so then you're like, what do I do? Well, we go to our equation, and we realize that the angle between these is 0, and sine of 0 is 0. So this is a good reminder to us that if the moving charge is parallel or anti-parallel to the magnetic field, the force is 0. This is a good reminder. There's no right-hand rule to use here. This is actually the first thing whenever you're finding the force in a moving charge to remember. If they are lined up with each other, nothing happens, which is kind of weird. It goes against every other force that you're familiar with in reality. Gravity, if something is moving in the direction of the gravitational field, it gets faster. Same thing for electric fields, faster or slower if they're parallel or anti-parallel. Magnetic fields, nothing happens. It's real weird that force is perpendicular, but I don't get to make the rules. You're going to have to take that up with someone else. I just explained them. The world is what it is. Whether you like it or not, this is how it be. All right, so the force is 0 down here. And by symmetry, the force on the top is also 0. What's the angle at top? On the top here, the angle is 180. Sine of 180 is also 0. Parallel or anti-parallel, the force is 0. So it does nothing. Woo, what an exciting problem. Good thing there's 2 more sides to this loop. What's the direction of the force for the right side of the loop? So we are looking at the right side, same exact loop. So on the right side here, the current is pointed up. I'm just circling it to denote which side I'm talking about. Is the force into the page? Is it out of the page? Is it 0 or is it to the left? What is the direction of the force on the right side of the loop? We'll go to 120. And these topics to me are some of the more exciting ones because we're finally getting into application of the physics concepts. It's all well and good to understand physics. That's really, I enjoy that stuff. But I think it's really cool when we can do stuff with it. And that's what this is going to get to. All right, we'll give 2, 1. All right, so warm up my right hand. Fingers are going to point up. I'm going to use that hand technique. My palm will point in the direction of the magnetic field, and my thumb, you can see I can nicely curl that. Thumb goes right into the page. For those online, fingers point up. I put my palm in the direction of the magnetic field. Thumb points right into the page. So if I draw that on here, points right into, remember an X is into it. So the right side is experiencing a force that way. I'm going to go ahead and duplicate this question because I think it's fun. I'm not going to give you the left side off the cuff. I'm going to make you work for it. What is the direction of the force on the left side of the loop? With the power of copy and paste, I have made a new problem. What is the direction of the force for the left side of the loop? So the right side, we just said, was into the page. What is the direction of the force on the left side? Here, current is going down. We'll go to 55 seconds. In 5, 4, 3, 2, 1. All right, here the current is going down. Palm still points in the direction of the magnetic field, so I can swing my fingers, woo-hoo. Thumb points out of the page. And it's the opposite, symmetry. Again, we really like our symmetry. When the current changes direction, the force will be in the opposite direction. So here it is out of the page, pointing down, magnetic field's there. So my thumb points out. And here's where we get to put it all together. Here's where we get to put it all together. Hopefully you kind of get the idea. I need something flat. Well, that is shocking. Somehow. Very few flat things in my backpack. Here is a beautiful Merry Christmas bag. It's so tiny. Anyway, so if the left side is getting pushed out. Let's see if I did it right. Yeah. Nope, in. If the left side is getting pushed in and this is getting pushed out, we get rotation, which may not seem very exciting to you all, but we literally just took electricity and magnetism and converted it into motion. We took electricity and just put some permanent magnets around it, and you can make something spin. And if you're creative, you can think of all sorts of applications for using electricity to make things spin. This could be used to make motors. This is one way of making a motor. Put two magnets. I'll clarify this in a second. Put two magnets, and then you have this clever little device here called a commutator. A commutator, I'm not going to test you all on this, so you do need to be able to figure out the direction that it would spin. Like that was important, finding the forces. I'm not going to test you on finding the torque on a current carrying thing, so just so you all don't get too stressed about this. But if I zoom in, if I attempt to zoom in and it doesn't work, whatever. There we go. No, it doesn't want to zoom in more. Press the picture. Oh, so devastating. Hey, there we go. This little commutator here is really interesting, and it won't let me zoom in on it. So I'm just going to make the slide look ugly and make this thing really big, and I'll fix it later. This little commutator, yeah, it's still awful. Whatever. It's got these little gaps in it. And the cool thing with that is as it spins, the direction of current will flip. Because if you think about that last problem, it'll actually, if you explore what will happen, it'll go 90 degrees, and then it'll kind of get stuck there. The forces will actually kind of just pull it outwards, and it won't actually make it spin anymore. But by doing this, you shut off the current for a bit, it'll keep spinning, and then you flip the direction of current. So instead of, where'd my beautiful Christmas bag go? Instead of this side experiencing a force this way, it'll experience a force the other way. And then you get it spinning and spinning and spinning and spinning, get it faster and faster and faster and faster. And do all sorts of interesting things with that. And you can control how fast it spins by supplying more current. Now, I will tell you this is not how electric motors work. It's actually the opposite. The current carrying wires, and we're going to learn that in the next slide, which we'll be able to start to explore. The current carrying wires are making the magnetic field, and they're causing a force on magnets. So basically just flip the script. Instead of having magnets on the outside that aren't moving and the wire moving on the inside, we have wires on the outside not moving. We'll see that at the end of the next presentation. But this is exciting to me because this is what lets us in society. This is what lets your blender work. This is what lets literally any device that you plug into an electrical outlet move. This is how we take electricity and convert it into motion, which is extremely important for us in today's society. Remember, I told you all that electricity is so special because it's basically liquid energy. It's energy that you can transport over long distances and then convert to useful forms. Heating, cooling, motion, like fans in your ceiling. But if you can't convert it to something useful, then who cares? And this lets us convert it into motion, which is your fans at home. That's motion, powered by electricity. Now you know how we can kind of do that on some level. Your speakers, your headphones literally are making a magnet wiggle. We're gonna have to kind of get to the next slide to see that, but it's still motion from electricity. And it's using these kind of principles. Literally any moving thing that gets plugged in, by the end of the next presentation, you'll be able to understand it. And if we can take electricity and convert it into motion, we should also be able to do the opposite. And that'll be what we learn when we get to Faraday's law. How do we take motion and convert it into electricity, which is the foundation of how we get every single bit of power that you all use, with the exception of batteries. So, extremely, even though I don't think anyone, if you're an engineer in this room, you're in the wrong class. Even though none of us are going into engineering and maybe if you build these things for a hobby, stuff like that, this is the foundation for our society. If you ask people how we get electricity, they say, a power plant. We burn coal. Okay, is that coal releasing electricity? No, it's not. You're going to actually learn how there's a step in between burning coal and electricity. And you all will get to actually understand that, which is, it's fairly foundational to society. It's fairly important. And 99% of people have no idea how to get it. 99% of people don't know how electric motors work, which is becoming the new norm. Electric vehicles. Pretty much most people know how a combustion car works. But how many people actually know how an electric car works, how it makes motion out of electricity? You will. Yay! Super useful, super interesting, even if it's not in technically your career. All right, so this is the first time where I've kind of actually we're going to jump to the next week's of slides just to introduce the concepts, the ideas, let you mull it over some. We have like 15 more minutes, so it shouldn't be too bad. But give you that bang for the buck, and this will be important for you all to do that discussion question. So it worked out nicely. So we've introduced the forces on magnetic fields. How do you make magnetic fields? And I will tell you, permanent magnets, yes, that is one way. But if you want to make really strong magnetic fields, you got to do it another way. And we'll kind of quickly explore that, do a few clicker questions. Just get an intro, kind of prep your brain, give you something to think over the weekend if you don't have enough to worry about as it is. Previous important concepts is basically everything the last slide needed. Vector, cross products, currents, positive charge moving, we just used all that. And then basically the two things I just taught you. What are magnetic fields that they cause force in moving part of, and that forces due to magnetic fields cause forces on moving charges. Literally everything we just covered. So hopefully that should feel very comfortable. In this slide, or in this week's step that we'll finish up next week, we are going to learn how to, this kind of gives away some of the punchlines here, calculate the magnetic field due to a current carrying wire, apply the second right-hand rule. Remember I warned you all there's like 3.5 right-hand rules. You got one down, 2.5 to go. Explain how parallel wires carrying currents can attract and repel each other, given this force, and determine the equation for the magnetic field in the center of a loop of wire. All right, fun. Let's connect what we just talked about to this section. To do that, we're going to talk about things that we're maybe a bit more comfortable with. So I want you all to brainstorm. What makes gravitational fields? Yeah, what makes gravitational fields? Think about it. See if anyone has, this one you can just holler out. What makes them? What do you need to make a gravitational field? You need mass. And what experiences a force due to gravitational fields? Mass. What makes a gravitational field? Mass. What experiences a force due to gravitational field? Mass. If you all did not learn this in Physics 1, every single object with mass has a gravitational field. Every single person in this room is causing a gravitational force on every other person in this room. You do not feel it because none of you are anywhere comparable to the size of the Earth. If you ever want to feel good about yourself, you've always got that. The Earth is way more massive, so you experience that. But if you were in space, two of you were in space, you would start to actually drift towards each other. You would be pulling on each other. All right, what generates electric fields? Something we learned about in this class. Let's hear that confidence. What is the thing that generates an electric field? Charges. And hopefully more of us feel confident now. What experiences a force due to electric field? Charges. Hopefully you're getting the idea. So, if the things that make gravitational field experience a force due to gravitational field, and the things that generate electric field experience a force due to that electric field, which of the following will generate a magnetic field using that logic? If the things that make a field experience a force due to that field. Is it stationary charges, moving objects with mass, or stationary objects with mass? What are the things that make a magnetic field? All right, and this is a good review, because the things that generate a magnetic field are the things that experience a force due to a magnetic field. We'll wait till 1:15. 5, 4, 3, 2, 1. So, what were the things that experienced a force due to a moving field? Well, if we just remember, it was Q, V, B. And the trick to this, it is moving charges. Nowhere in that equation did we see mass. Now, yes, technically everything that has charge has mass, but it's not the mass that's the one experiencing the force. It's the fact they have charge. If I have a neutron moving, a neutron has no charge, it will experience no force due to a magnetic field. That's how we know that it's the charge. We have the counterexample of a neutron. I can shoot a neutron through a magnetic field and nothing will happen. If I shoot a proton or an electron, it'll bend. That's one way of kind of isolating particles. So while yes, technically protons and electrons do have mass, so do neutrons, and those aren't affected. So, very important. So the things that experience a force generated. So, if I have a current carrying wire, I can make a magnetic field, and yay, right-hand rule number 2. Give you something to kind of confuse you for a bit over the weekend. We'll do a couple more practice after this, and then we'll probably be good. Let's see if I will end up introducing the equation. No, not quite. All right, so we'll do this. We'll do a couple practice, and that'll be good to go for us. So, right-hand rule number 1 gave us the force on a current carrying on a moving charge. Right-hand rule number 2 gives us the direction of the magnetic field due to a wire. It's kind of handy that all the rules are using our right hand. Not handy. Isn't that good? That wasn't on purpose, and I'm still okay with it. Right-hand rule number 2 will give us the direction of the magnetic field. Point your thumb to the direction of the current. I'm going to kind of switch these rules a bit. Point your fingers kind of where you want the magnetic, where you want to find the magnetic field. I'm kind of adjusting what I said here. Both of the rules I'm going to say were thumb in the direction of current, point your fingers where you want to find the magnetic field, and then turn them 90 degrees. And then turn them 90 degrees. Be careful not to over-rotate. Your finger should point 90 degrees. So, let's look at this one here. Here, I kind of did the opposite. I kind of switched rules 2 and 3, but current is up. Say I want to find the magnetic field on the right side of it. Put my thumb up, flat hand, I point my finger in that direction, I turn my fingers 90 degrees, bam, into the pinch. That'll tell you the direction of the magnetic field at that point. Point your thumb up, point your fingers in a flat line. So for those online, thumb up, fingers where I want to find the magnetic field, and then turn them 90 degrees. Turn them so you got a nice little right angle there. If I want to find the magnetic field on the other side, same thing. Thumb up, fingers that way, turn 90 degrees, it points out. And if you do that everywhere, say we do it here, it's going to be here, you find that the magnetic field that a wire generates is a circle. It makes a circle around it. The farther away you get, the weaker it'll be. We'll find the equation for that in a second. But the magnetic field around a current carrying wire is a circle. a bunch of different circles, each with a constant magnetic field at that radius. So there's the magnetic field there. Everything on that circle has that magnetic field. Everything on this circle has that magnetic field. And they get stronger and stronger as you get closer and closer. Let's practice. Find the direction of the magnetic field at the point given due to the current shown. So this one's got 2. So much fun. 2 to practice with, and the one on the right's got 2 to practice with, and that'll be good enough for today. So, thumb in the direction of current. Current here is to the right. Let's find point A first. So thumb in the direction of current, that's to the right. Point your fingers up. You are going to have to rotate your wrist again so that your fingers can actually point up. Make certain your thumb keeps pointing the same way. So, my thumb is to the right. Flat hand, my fingers point towards A. 90 degrees. Keep my thumb pointed that way. Turn my fingers 90 degrees. Into the board. So, flat hand, thumb in the direction of current, point your fingers towards it, 90 degrees. So, that gives you into the page on the top. And you could guess symmetry what the bottom's going to be, but good practice nonetheless. For those online, thumb pointed in the direction of current, fingers pointed towards A, turn your fingers 90 degrees, bam. Point B, same thing, point your thumb in the direction of current. I want my fingers to point, B is down here, so I gotta do some contortioning, because I gotta, it's all over here. And then, 90 degrees, point it under the board. Make sure you keep that 90 degrees. Obviously, if you do, that's more than 90 and it's wrong. So, your fingers and your palm should make a 90 degree angle. Your fingers and your palm should make a 90 degree angle at the end. So, thumb down towards that, B points out of the board. And again, that's because it's going to make a circle. The magnetic field kind of makes a circle around this. All right, C and D, same thing. Last one we'll do. Thumb pointed down, flat hand, and then I point towards C, because that's the point I care about, and into the board. So thumb pointed down, C, into the board. And at point D, thumb down, out of the board. Okay, there you go. Fun fact, everywhere on the left side it's going to be out of the board. Everywhere on the right side it'll be into the board. Or sorry, everywhere on the left side will be into the board. Everywhere on the right side will be out of the board. Okay, so let me just do a quick wrap up. I know I've got 2 slides with the wrap up, so I'm just going to jump to the one over here. So what did we learn today? Main points number 2. We learned that magnetic fields cause forces on current-carrying wires. F equals ILB sine theta, where theta is the angle between them. We then learned that if you have a loop of wire in a specific orientation, it will spin in a magnetic field. It will experience a torque which will cause it to spin. I'll clarify that. It will experience a torque which causes it to spin. So, next class we'll finish up with, next week we'll finish up with the stuff about current carrying wire. We'll introduce equations for calculating it. And we'll explore again. Of course, if we just have one single wire, we'll make it more complicated. We'll do a loop, and then what happens is we have a lot of loops. You know, we start with a simple concept and build. That's how physics works. Because then it lets us do cool things. If you all have any questions, got a few minutes, come on up as usual. Good luck on the DC circuits. Do this Saturday. Quiz. DC circuits quiz due this Saturday. Yeah. Oh, I'm sorry. Yeah. Let me hop over here. For the one I just covered? Okay. All right. Okay. All right, online people are going in the stream. They're asking me, someone's asking me to show it in class, which you won't see anyway. If you have any questions, of course, email me.